Hello, and welcome to my presentation on predicting nuclear fusion ignition. This presentation is predicated on the nuclear fusion breakthrough realized in 2022 at the National Ignition Facility right here in the United States and the subsequent artificial intelligence models developed to aid in the process of deep learning and analysis. A pivotal milestone in the field of nuclear fusion is achieving ignition. This is the point at which fusion generates more energy than what's supplied to initiate it. Researchers at the National Ignition Facility have made historic progress since their initial net energy break-even in 2022. Since then, there's been a focus in the complexity of inertial confinement fusion. For decades, fusion experiments have consumed far more energy than they've produced, and we've yet to quantify a viable solution for containment. The ultimate goal of this new focus is ignition. This is the defining factor of fusion success. It's where the nuclear reaction becomes self sustaining and produces a net gain of energy. By utilizing artificial intelligence models offering quasi reliable guidance, it's allowed researchers to more effectively design potential experiments and assess the impacts of upgrades. Enhancing the predictive power of researchers through AI's deep learning, this represents a critical advancement for the physicist community. It represents a fundamental shift in methodology, and this is for a field that has traditionally relied on decades of iterative experimentation and complex but not always predictive simulations. Now, quantifying ignition probabilities starts with several things. One of them is physics simulations, which is a model that's grounded in established principles of radiation hydrodynamics, ledgering, leveraging vast ensembles of complex computer simulations that model the physics of fusion implosions. That also includes experimental data to refine accuracy and account for real world complexities, and the Bayesian statistics, which is an inference framework that was employed to systematically combine the simulation results with the empirical data. And this allows the model to quantify uncertainty and generate probabilistic forecasts. And as of today, those forecasts are exceeding 70% probability. Now, the fundamental barriers to fusion is forcing the atomic nuclei to merge. And since all nuclei are positively charged, they naturally repel each other. And that's with incredible force called the Coulomb barrier. To overcome this repulsion, we must replicate the conditions that are found inside of our very own sun, but even with a slight more intensity. And at the same time, we also have to achieve a form of stabilization with the nuclei through confinement. And as of today, there are two methods in which this takes place. One of them is magnetic confinement. And this method utilizes powerful magnetic fields to create a magnetic bottle of sorts. And that holds the plasma in a donut shape, which is called a tokamak. The second method is inertial confinement. This method utilizes incredibly powerful lasers or particle beams that rapidly heat and compress a tiny pellet of fuel. And that fuel implodes, creating necessary temperature and the density needed for the brief moment of fusion before it blows itself apart. This inertial confinement method finally reached scientific break even at the United States National Ignition Facility for the very first time in history back in 2022. We're making progress. The core physics of nuclear fusion is well understood. It powers the sun, after all. Now, the challenge shifts from the scientific question of can it work to the massive engineering and theoretical science conundrum. How can we build a durable and economic power plant that can achieve viable and long lasting nuclear fusion? The path forward involves tackling several critical challenges simultaneously. And this is primarily focused on building and learning from larger, more powerful experimental factors. The final hypothesis in nuclear fusion isn't a single unproven idea, but rather a widely accepted goal. And that's to prove that fusion can be commercially viable, safe, sustainable, and a net positive source of energy here on Earth. The core physics is well understood. It powers the sun, after all. So the challenge is shifted from the scientific question, can it work, to how can we build it to be durable and an economical power plant that actually does make it work. And the last and final step, number four, is engineering the fusion power plant to make this a reality. And finally, I want to thank everyone in advance for their input into this study. For any questions or comments, I can be reached through my website at timfogle.com. Thank you very much to the Liberty University staff, including Mr. Professor Anthony Reed, and everyone else who provides input into this presentation. I look forward to hearing your comments and responding to any questions. Thank you.